Normalization. Lessons 2.4. Boyce Cobb Normal Form, BCNF. In these lessons, the basic concept of Boyce Cobb Normal Form, BCNF, will be explained, and you will understand how to convert the table to BCNF. Based on functional dependency that takes into account all candidate keys in a relation. For a relation with only one candidate key, 3NF and BCNF are equivalent. A relation is in BCNF if and only if every determinant is a candidate key. Violation of BCNF may occur in a relation that contains two or more composite keys, which overlap and share at least one attribute. From 3NF to BCNF, you should identify all candidate keys in the relation, and you should identify all functional dependencies in the relation. If functional dependencies exist in the relation where their determinants are not candidate keys for the relation, you should remove the functional dependencies by placing them in a new relation along with a copy of their determinant. The following are the characteristics of BCNF. Let R be a relation schema, X be a subset of the attributes of R, A be an attribute of R. R is in BCNF if, for every functional dependency, X functionally determines A, one of the following is true. A is a subset of X. X is a trivial functional dependency, or X is a superkey. Theoretically, we must check each functional dependency. X functionally determines A in F plus. It is actually sufficient to check whether the left-hand side of each functional dependency in F is a superkey. An easier definition: every determinant must be a candidate key. Then I will show you a testing for BCNF. In a relation schema R, A, B, C, D are the attributes of R. With functional dependency, A functionally determines B, B functionally determines C. Decompose R into R1 containing A and B, and R2 containing A, C, and D. Neither of the dependencies in F contain only attributes from A, C, D. So, we might be misled into thinking R2 satisfies BCNF. In fact, dependency A functionally determines C in F plus, so R2 is not in BCNF. R2 containing attributes A, C, and D with functional dependency A functionally determines C is not trivial, and A is not a superkey. Therefore, R2 is not in BCNF. Do you still remember this example? You have seen this example in the last two lessons. Now I will also use this example to show you how to check if the database is in BCNF. To check if the database is in BCNF, you have to check every functional dependency fulfill one of the following conditions. A is a subset of X, or X is a superkey. There are the functional dependencies of the examples. Student ID functionally determines student first name and student last name. Course code functionally determines course name. Student ID and course code functionally determine teacher ID and grade. Teacher ID functionally determines teacher first name and teacher last name. Then we will check if this functional dependency fulfill the two conditions one by one. For the functional dependency, student ID functionally determines student first name and student last name. This is a trivial functional dependency because the attributes student first name, student last name are not a subset of primary key, and student ID is superkey. For the functional dependency, course code functionally determines course name. This is a trivial functional dependency because the attribute course name is not a subset of course code, and course code is super key. For the functional dependency, student ID and course code functionally determine student ID and grade. This is a trivial functional dependency because the attribute is not a subset of the primary key, and the primary key is super key also. For the functional dependency, student ID functionally determines teacher first name and teacher last name. This is a trivial functional dependency because teacher first name and teacher last name are not a subset of teacher ID, and teacher ID is super key. Therefore, the example is in BCNF. Lossless join decomposition is one of the methods to convert the table to BCNF. Given a schema R, W is a subset of R. A is a single attribute. W functionally determines A is a functional dependency that violates BCNF. Decompose R into R minus A and WA. If either is not in BCNF, decompose recursively. The decomposition is lossless join. This is the example of BCNF decomposition. Let R be the relation schema. Branch name, branch city, access, customer name, known number, and amount are the attributes of R. The functional dependency of R contains branch name functionally determines access and branch city, and known number functionally determines amount and branch name. The key for R are known number and customer number. We should handle one of the functional dependencies first. Branch name functionally determines access and branch city. Branch name is W, access, and branch city is A. One of the tables should contain WA. In R1, it contains branch name, branch city, and access. And in the other table, it should contain R minus A. R2 should contain branch name, customer name, known number, and amount. Then we will handle another functional dependency. Known number functionally determines amount and branch name. Known number is W, amount and branch name are A. One of the tables should contain WA. Therefore, R3 contains branch name, known number, and amount. And the other table should contain R minus A. Therefore, R4 should contain customer name and known number. In these lessons, you have learned about what is BCNF. That's the end of the lessons. Thank you.